Hello, everybody. Welcome to the final lecture for GL 101. This is a brief summary of the Earth's history. And so in the last lecture, we talked about how we put different geological events in order based on what we see in the rock record, and how we assign those different ordered events to specific time periods based on radiometric dating and the decay of certain elements that we find within the rocks. And that's called absolute age dating. And once we've done all of that, now we can kind of piece together a story of the Earth as a whole, both how the Earth itself evolves and how life on Earth evolves. So let's get started. So we've all heard about evolution as it pertains to biological life and sort of biological structures and systems over time. But evolution, sort of generally defined is change over time, right? And so all of the Earth's systems, the atmosphere, hydrosphere, geosphere, and biosphere, have all evolved together. And each part of that system affects the other in pretty profound ways. The biosphere over here, including animals and other organisms like plants and bacteria, they can produce oxygen, which will affect the atmosphere. They can produce fossils, which affect the geosphere. They can change the chemistry of the hydrosphere, so oceans, lakes, rivers, etc. And so biology plays a huge part, and the rest of the Earth plays a huge part in the evolution of biology as well. And so all of these systems do evolve together and have evolved together. And it's important to think of the Earth as this kind of larger dynamic system that incorporates these four main components, all kind of working together to produce the environment that we find today. So I think a natural place to start when we're telling the story of the Earth is the formation of the solar system. And some of this may be review from the first lecture in the class when I was doing a kind of brief summary of everything that you'd be learning. And obviously the universe, scientists believe, started with the Big Bang, and that produced an expanding gas cloud of helium, hydrogen, and trace other elements. And that began to expand and separate into protogalactic clouds. And all of this is held together by gravity, and all things that are kind of floating in the vacuum of space produce some kind of gravity, whether it be the size of a grain of sand or the size of a gigantic sun. And as such, things are pulled together in the vacuum of space at every level. And so gravity is the dominant force there. And about 5 billion years ago, there was a supernova that caused a gas cloud that formed our early solar system. And this began to spin and collapse in on itself. So here's what would happen. So you've got this big gas cloud here, and it began to spin and collapse in on itself, as these arrows show, and then eventually formed a solar nebula or a protosolar disk. And that disk is just a kind of central space here where things are being pulled together by gravity very strongly. And then everything else out here in this disk is separated by density and mass. And the more massive things are going to be pulled towards the center, and the lighter elements and lighter gases are going to be out circulating around the outside. So for most solar systems, their formation involves this collapse at the center, which generates humongous temperatures and pressures and initiates thermonuclear reactions. And thermonuclear reactions in this case are hydrogen atoms that fuse together to form helium atoms. And this produces heat and light, and that's what's put off by all stars. And this is fusion as opposed to fission. So most nuclear reactions that we've produced here on the Earth are as a result of fission or splitting atoms, whereas in a solar context, we're actually getting fusion, where we're fusing hydrogen atoms into heavier helium atoms and beyond. So in the center of the sun, we're fusing helium into lithium, and lithium into something even heavier, and so on. And so as that cloud continues to collapse, it forms the sun's interior, and then all of this circulating gas and dust and rocky bits starts to form the early protoplanets. And so rocks and metals that have higher melting temperatures tend to condense closer to the sun, forming the inner rocky planets. As seen here, we've got the four: Mercury, Venus, Earth, and Mars. And the more volatile or low boiling point compounds like methane and ammonia condense in the cooler exterior, further away from the solar nebula, and they create the outer gas giants. And Pluto is an exception here. It's a rocky planet, dwarf planet rather, that has an inclined orbit, so it doesn't follow the same orbitals that the 8 major planets in the solar system do, where they all kind of sit in a linear ellipse around the sun. Pluto kind of dives in at an angle. Sometimes it's between Uranus and Neptune, and sometimes it's outside of that. And so the going theory here is that it was a wandering planetary body that was captured by the sun's gravity at some point and became incorporated into our solar system, but it's not properly a planet. So as far as the formation of the rocky planets, and specifically the Earth, it formed again from accretion of material in the solar nebula. So in that solar nebula where we still had the gas still accreting, you can imagine that things of similar densities and similar masses are going to be in similar orbits or distances from the sun. And so as those things are spinning around, the larger pieces are accreting the smaller pieces within that orbit. And eventually everything has enough time to run into one another. Think race cars around a track. Eventually all the race cars might catch up with one another. And when they do, they might have a big crash. Same thing happens here. All of those rocks that are in a specific orbit, whether it be Venus's orbit or Earth's orbit or Mars's orbit, they all eventually collide with one another. And once that's done and there's nothing left to collide, that's when we consider the Earth or Mars or Venus as having cleared out its orbit. And that's when the planet cools down. It's no longer being bombarded, and so it starts to cool down, and that's when processes begin to happen on the surface. The accretion and decay of radioactive elements, in addition to the initial heat of the early bombardment as Earth was clearing out its orbit, that produces the heat and melting necessary for us to have a mantle and a liquid core and things like that. The heavier elements, nickel and iron, sink to the very inner portion of the planet, and that forms the solid core. And then the lighter crystalline materials like silica and aluminum and certain gases and etc., that all begins to float to the outside, and that forms the rocky mantle and eventually the crust and atmosphere. And here's what a lot of those early rocks would have looked like. This is from a meteorite. This is what much of the early solar system's rocks would have looked like as they were colliding together. So when the Earth first formed, it started to outgas carbon dioxide, water vapor, and nitrogen, creating the early atmosphere. And as the planet cooled, that water vapor began to form clouds, and those clouds began to precipitate rain. But it's very important to keep in mind here that we needed to have sufficient cooling on the planet so that the atmosphere could form and that solid crust could begin to form. Okay, so This is, maybe, a couple million years into the cooling of the Earth, and about 4.5 or 4.45 billion years ago, we started to see the evolution of the atmosphere. And as the Earth formed solid, cooler crust, that rainwater began to collect on the surface and form oceans. And that reduced the water vapor in the atmosphere. Then carbon dioxide followed, which dissolved into the surface water. So that means that the remaining atmosphere was mostly nitrogen rich, as oxygen and hydrogen and carbon dioxide began to interact with the water at the surface. Okay, and so the modern atmosphere, as I've discussed, is about 80% nitrogen and 20% oxygen, with then a bunch of other trace elements and compounds like carbon dioxide, and sulfur, and methane, things like that, making up roughly 1 to 2% that's left over. So as far as the evolution of the atmosphere, this is what kind of fostered in early life. So the first plants to use light from the sun to make food sugars and carbon dioxide and water in a process called photosynthesis was the byproduct, as that happened, the byproduct of photosynthesis is free oxygen. So the oxygen that was bound up with hydrogen as water vapor, through the process of photosynthesis, plants break down carbon dioxide. They use the carbon to make sugars along with the hydrogen, leaving behind just oxygen that gets respirated out as the plant sort of exhales, if you want to think about it like that. And plants and early bacteria began to slowly add free oxygen to the planet's atmosphere. And this all happened during a time we call the Precambrian, which is a huge amount of time relative to the rest of Earth's history, and is somewhat of a mystery because we don't have any fossilized life necessarily from that time outside of just clumps of bacteria. So not much is known about it. We do have lots of rocks from that time, but most of them are buried beneath later sedimentary rocks and or have been altered by metamorphism due to tectonic activity. So we have kind of the beat up remains of these early protocontinents and ocean sediments and things like that. But the Precambrian represents about 4 billion years, or 88% of the Earth's history. It's the least understood, like I said, because A, little to no fossils to help us correlate or determine paleoclimates. So we're not necessarily sure what kinds of climates we had during that time. Precambrian rocks are usually strongly metamorphosed and deformed, like I said, so many of the environments of formation, whether they be igneous or sedimentary, have long since been metamorphosed, and so it's tough to say what the initial conditions were like. And again, like I said, Precambrian rocks are buried from view by Cenozoic, Mesozoic, and Paleozoic sedimentary rocks. But those early Precambrian rocks do form the cores of many of the continents, and these are huge areas that are deformed metamorphically, and we call these shields. And in North America, we have the Canadian Shield and the Greenland Shield. The Canadian Shield does stretch down into parts of the UP and then parts of Minnesota, Wisconsin, and the Dakotas. And you can see that there are other shields, the early Brazilian Shield, African Shield, Indian Shield, Australian Shield, and then some parts of Northern Europe and parts of Siberia and Central Asia also have some of these early shield rocks. And these are sort of the proto-continents. Everything else that you see here in brown and beige were later accreted to these over geologic time during basically the Precambrian all the way up to today, where that is still taking place, although very slowly. Precambrian rocks have a large number of ores and resources that we mine. So nickel, iron, gold, silver, copper, chromium, uranium, diamonds, all this stuff comes from Precambrian rocks. The Earth was running a little bit hotter back then, and so these heavier ores, metallic ores, were heated up and a bit less dense, and so they found themselves on the outer edges of the mantle in a lot of respects, or being pushed up by hot spots or mantle plumes. And so we find a lot of those ores incorporated into the crust. That process isn't happening so much these days. That was all happening during the Precambrian, when we had sort of ultramafic volcanic activity and ultramafic plutonic activity. Banded iron formations are sort of the famous formations that we have in the UP and parts of northern Wisconsin and parts of northern Minnesota. So this is when there was a lot of iron dissolved in the ocean, and there wasn't a lot of oxygen in the atmosphere at the time, so it remained dissolved. But once stromatolites and other bacteria and early plant life began to oxidize these materials, they began to rust and deposit at the ocean floor in sediments. And that produces these beautiful formations of layered iron and quartzite, or sorry, not quartzite, quartz in the form of jasper, cryptocrystalline or microcrystalline quartz, similar to the cherts you had in your mineral kit. And so we see these beautiful banded formations of iron and then jasper and then iron and then jasper, and in some places like the UP, these have been deformed by tectonic events, and then certain other places like northern Minnesota, we still see them deposited horizontally. Precambrian fossils are incredibly rare because most of the life then was bacterial, or life we call archaea, which is now extinct bacteria that were more prevalent during the Precambrian. And they're mostly soft-bodied and primitive organisms, so they didn't fossilize very well. Most of the stromatolite fossils we have are a result, like I said in the last lecture, of these organisms incorporating sediment into their structure. And so that sediment is preserved today, whereas the biological structures that they formed, namely the bacterial structures, have long since decomposed or disintegrated. Again, like I said, they're formed from algae, and they form these like small mounds. And we do still have some stromatolites present on the planet today. What I'll say is that these fossils were not common until about 2 billion years ago. So life probably got going much earlier than that, maybe 3.5 billion years ago. But we don't have really good preserved structures until they started to form these stromatolite colonies at about 2 billion years. So it took a long time, about 1.5 billion years, for them to get to this point. So life started fairly early, but it just kind of slugged along, not evolving much for most of the Earth's history. Okay. This is what stromatolites would have looked like, and this is what they look like today. This is in Shark Bay in Australia. The reason that these guys aren't really around anymore is they evolved during a time when there were no predators to speak of. The only threats that they necessarily had was environmental. And unfortunately, their biggest threat was themselves, because they were able to produce so much oxygen from photosynthesizing in the water that they fundamentally altered the chemistry of the atmosphere on the Earth forever. They produced so much oxygen based on the breakdown of water that they basically weren't able to breathe anymore. And there's only a few spots on the Earth now where the conditions are just so that the water is very saline, the water is closed off in these bays from any kind of predators that might come and attack them. And so they're still around in just these like a couple little spots and pockets on the Earth. This is what they look like. And then this picture over here is their sort of bacterial cousins or ancestors. And again, we do have evidence for microscopic life extending back to about 3.5 billion years. We find those a lot in these chert nodules here, but sometimes we find them in dolostones or dolomite. Notable locations for these are Australia, where we have 3.5 billion year old bacterial fossils, Southern Africa, 3.1, and Gunflint Chert of Lake Superior at about 1.7 billion years ago. More advanced organisms and primitive plant fossils and fossils from animals can be found in the late Precambrian, but there was kind of the explosion of multicellular life at the end of the Precambrian, and that's what we use to define that boundary between the Precambrian, which is the first 4 billion years of the Earth, and the Cambrian, which starts at about 550 million years ago. So at the end of this Precambrian period, fossil records show lots of diverse and completely multicellular organisms kind of exploding. And that sets the stage for the Phanerozoic era. And that is that's kind of Latin and or Greek for life revealed. So that's the eon after. So we tend to think of the Earth's history in 3 main phases. There's the Archean, which is part of the Precambrian. And the Archean is early, probably not a lot of life, maybe some single-celled bacteria, not forming those colonies yet. Then we have the Proterozoic, which makes up the second bit of the Precambrian. And that's early life, Proterozoic. So zoic means life, protero means like proto-life. And then the Phanerozoic means life revealed. And we are in the Phanerozoic now. And it started again at the Cambrian at about 550 million years ago. Here's a breakdown of what I just discussed. So here's the Precambrian here. We've got the Archean here. Some people break the Archean up into 2 and call the early Earth the Hadean. This is when the Earth was mostly molten, right, from that early bombardment as it was clearing out its orbit. And Hades is Greek hell, and so the Hadean would have been kind of a hellscape, right? Think just like lots of volcanic activity, almost a molten outer surface. Then you have the early, middle, and late Archean from 3.8 billion years ago to 2.5 billion years ago. Then you have the Proterozoic from 2.5 billion to 550 million. And all of this makes up that Precambrian. And that just means before the Cambrian, right? Then we have the Phanerozoic, which makes up the rest of this here. And if we look over here and zoom out, here's the Precambrian, all tiny over here. We've got the Paleozoic portion of the Phanerozoic, which makes up the Cambrian, Ordovician, Silurian, Devonian, Mississippian, and Pennsylvanian. Both of these together are called the Carboniferous. And then the Permian. Then you have a mass extinction event, and then you've got the Triassic, Jurassic, and Cretaceous. That makes up the Mesozoic. Then you have a mass extinction there, and then we have the Cenozoic. And that can be broken up into the Tertiary and Quaternary, and those have these smaller epochs included within them. And here's the time spans that we're talking about. So the Paleozoic era is where life explodes. That happened at about 540 million years ago. And again, it's divided into the Paleozoic, Mesozoic, and Cenozoic. The Paleozoic, which means ancient life, are the first life forms with hard parts, so bones, shells, teeth, and scales. And we call this the Cambrian explosion. So there was no multicellular complex life before that. Then all of a sudden in the fossil record, tons of differentiation of different structures and body parts and tissues. And the going theory now is that this is the result of this little critter over here. This is a little portion of your cell. Every living cell has some of this in it. This is called mitochondria. And if you look at a mitochondria, and if you look at its DNA, it has DNA that is different from yours. So all your cells have DNA that replicate and produce new cells, and so your DNA is very specific to you. And every cell in your body, from your skin to your hair to your liver to your toenails, all has DNA in it, right? Every cell also has mitochondria in it, and mitochondria have different DNA. they evolve within your body, and they've evolved separately within your body from you over you know, over your lifetime, over the lifetime of all life on the planet. And so the going theory now is that when there were little single cells kind of bumping into each other, mitochondria would have been one of those single cells, and it got incorporated into another cell, another bacterial cell, and it started to do its own thing in the fact that it started to produce energy for that cell. And so most bacteria and single-celled organisms are kind of running around. Mostly they only have enough energy to eat and reproduce. And they reproduce through cell division, right? It's not sexual reproduction. And so they really only have enough energy to eat and split, eat and split, eat and split. Well, once these mitochondria came along, they got incorporated into some cell, formed a symbiotic relationship with that cell, and the mitochondria basically said, hey, you give me what I need, and I'll give you energy, right? And so this allowed those cells that had mitochondria incorporated into them to basically utilize this new powerhouse of mitochondrial cellular life within its own cell. So now it could, it had a store or a surplus of energy, and so now it could start to develop new structures over vast geologic time. It would mutate and adapt new structures that allowed it to begin to exploit the environment in new ways. And so now, rather than just eating and dividing, now it could use this weird new growth that it had to capture a certain kind of foodstuff, or it might be able to produce some kind of photosensitive receptors on its surface that allowed it to understand when it's in dark environments and light environments, and that allowed it to exploit the environment in different ways to get food. And so this is where we really start to see tissues forming and more complex structures within these early organisms. And that probably produced cells that started to work together in different tissues and started to produce different body types and shapes. And that might be what's responsible for the Cambrian explosion. So geologically speaking, for most of the Paleozoic history, the continents were assembled into one large continent, Gondwana land, that resided in the southern hemisphere, more or less, with Western Africa near the South Pole. North America and Europe were thought to be pretty much near the equator, and most of the life during the Paleozoic was in the oceans. So this is when ocean life really took off. So on the continents, North American would have been fairly barren, lowland, inundated with several times by shallow inland seas that produce a lot of the sedimentary rock that we see in North America, especially up here where we are in the Midwest, because we're close enough to the Canadian Shield that most of the continent, the outer edges of the continent that would have been inundated by these shallow inland seas are right where we are now, kind of around the Great Lakes, and then up north, north of the Canadian Shield, in parts of northern Canada and western Canada. And these early oceans would have evaporated, leaving behind a lot of the evaporite deposits that we have underneath Grand Rapids, as a matter of fact, like all those gypsum mines. That would have been a result of some of these early seas. And also we started to get early orogenies, so continents, these kind of proto-continents or shield continents coming together, and when they ran into each other, they started to form mountains. As they were forming Gondwana land, most of these mountains were beginning to form. Okay, and that's shown here by these darker brown splotches here. So these were mountains that were formed from the accretion of different volcanic island arcs accreting onto these early shields. We started to get mountain building. Many of these mountains have long since eroded, with the exception of the Appalachians, which are experiencing enough rebound that they're actually higher now. They should be eroded down to nothing because they are super duper old. But there's enough uplift there due to some other geologic forces that the Appalachian Mountains are still protruding up above the crust there in ways that many mountains their age no longer do. So early Paleozoic life was entirely invertebrates, so creatures with no skeletal system or spines. They were dominant, and here we have trilobites, brachiopods, and cephalopods. And cephalopods are sort of the early ancestors of squid, octopus, and nautilus. This is the first time we see in the fossil record creatures that began to secrete shells or hard parts for protection, and also for acquiring foodstuff and supporting their body mass. As you may have learned earlier in your academic career, many of the invertebrates have that kind of outer shell, and that shell really encases the softer body of the animal within it, right? And so that's how it maintains its structure. Otherwise, they just kind of be blobs of flesh floating around. So these shells are super duper important for early life. And as we move through the late Paleozoic, we start to get the formation of the supercontinent Pangaea. And during this time, so the Devonian, this is when we start to see vertebrates evolve en masse in the ocean, and these are early fish. So fish are vertebrates, they have spines and skeletal structures, and so they would have been the earliest vertebrates. And really the Devonian is the age of fish at about 410 million years ago. Then we started to get the collision of North America and Africa, forming the Appalachian Mountains here during the Mississippian at about 330 million years ago. And that's right here, you can see that. And at the end of the Paleozoic, we had the Permian extinction. This is at the end of the Permian. This is also called the Great Dying. So during the late Paleozoic, we had land plants developing. Fish started to develop scales. The first sharks appeared. Certain fish began to adapt to land, so they started to evolve into amphibians, similar to frogs, right, that we see today. And amphibians rapidly diversified, some starting to become a little bit more reptilian here. And eventually, they began to exploit the land in more constant ways, right? So they started to become true land-dwelling reptiles. There would have been large tropical swamps that extended across North America, because again, we're at the equator. But also Europe and Siberia, we're also experiencing these kinds of climates. And these swamps are where we get most of our coal deposits that we have in North America and Asia and Eurasia. And this is from those tropical swamps. Lots of terrestrial plants would have fallen down into these swamps and built up over time. And these swamps were anoxic, right? So the stuff wasn't decomposing. And so that carbon was just collecting at the bottom of these wetlands and slowly forming the carboniferous deposits that form coal today. And again, like I said, at the end of the Paleozoic, we get that mass extinction event. Here's some pictures of the types of life that we would have seen in the late Paleozoic and middle Paleozoic. So here's the Devonian, lots of fish developing. The late Paleozoic, we started to get amphibians, and we started to get reptiles on land, and lots of land plants evolving. And for an overview of sort of the timeline of the different species that we see on the Earth today, we can kind of look back, and this is a sort of cartoonish overview of when things started to differentiate into those different invertebrates, vertebrates, and plants. And one thing I want to point out on this slide is that these dotted lines go down here and then they just kind of end, but that's not at all how things actually went. These dotted lines would have all eventually kind of started at some single point, and they began to branch out from a single common ancestor. All living things on the planet do have common ancestors, and as the tree of life sort of branches out, where two branches split off, that's kind of where a common ancestor would be. So everything has a common ancestor, but invertebrates and reptiles might have a common ancestor that came later, and reptiles and amphibians have a common ancestor that came even later than that, and amphibians and fish have a common ancestor that might have come before or in between somewhere. So, similarly, mammals and birds have a common ancestor somewhere, but mammals and reptiles and amphibians have a common ancestor somewhere down here. So when people say, oh, well, we evolved from apes, they're right to be skeptical about that because we didn't evolve from apes. We are apes, and we have a common ancestor with all other apes on the planet, right? The other great apes. Similarly, we have a common ancestor as apes with monkeys and with shrews and with dogs and giraffes and elephants and trees and whales and everything else. So, and those common ancestors would have had, like for, let's say, mammals and amphibians or reptiles and fish, for reptiles and fish, we would have had a common ancestor that looked a bit like a reptile and a bit like a fish, maybe like an amphibian, right? And mammals and birds would have had a common ancestor that looked a bit like a modern day bird and a bit like a modern day mammal. And similarly, mammals and reptiles would have had a common ancestor that looked a bit like a reptile and a bit like a mammal, right? And then there was a split there, and different mutations and different selective pressures would have caused those things to begin to evolve separately and away from each other. And eventually that produces all the current life that we see on the planet today. And the width of each one of these little kind of blobs tells us kind of what's more prevalent on the planet today relative to other things. So lots of invertebrates, not so many reptiles and amphibians, lots of mammals, a fair amount of birds, lots of fish, lots of flowering plants, etc. So here I'd like to talk about how we separate different geological periods. And over here on the right is sort of an overview of the last 600 million years. And it's showing a steady increase in the number of families present on the Earth. And I don't mean families like your mom and your grandma and that sort of thing. What I mean here is the Linnaean classification of organisms, family in that sense. So up here we've got domain, that's eukarya, that has to do with your cells. Are you a bacteria or aren't you? Kingdom has to do with, are you a plant or an animal, right? So here's a cat, here's you. You're both Animalia. Phylum, you're both Chordata. We both have spinal cords. Class is Mammalia. We're both mammals, right? This is where birds and reptiles and stuff would branch off and have a different class. Order is Carnivora, right, for cats, and we've branched off from that as primates. So we're in the primate order. They're in the Carnivora order. And then family is the next one down. So Felidae means that's where cats actually start to separate out from other carnivora. And Hominidae, where hominids, namely humans, start to, or human-like creatures, start to branch away from other primates. And then after family, you've got genus with Felis here and Homo, us, that means same. And then species, this is Felis catus, and we are Homo sapiens. So that's what I mean here by family. That's what this line is. And here we can see that up until about the end of the Ordovician, we had a fairly steady climb in the number of different families, about 400 or so. Then we see this sudden drop right here. So this is extinction event 1 at the late Ordovician, and that we lost about 12% of diversification of different family types. Then things kept going until the Devonian. At the end of the Devonian, we have another extinction event, and that's we lost about 14%. Then we keep going here to the end of the Permian, and then we have a very large extinction event. About half of the species on the planet disappeared. And that's the great dying that I mentioned. That's the Permian extinction. The largest extinction event in Earth's history, although we are getting pretty close to it now. We are currently in an extinction event caused by us, right? By man, so our humans. And so we might surpass that as far as the amount of species that are wiped out all at once, or not all at once, but geologically speaking, very much all at once. And that's why a lot of times the end of the tertiary here, we've now officially started to call it the Anthropocene, which is age of humanity. And we're seeing a mass extinction event there as well, sadly. But then at the Triassic, at the end of the Triassic, we have another extinction event here. That's 4. And then finally 5 at the end of the Cretaceous, which saw the end of the dinosaurs at about 60 million years ago. That's the last major extinction event in the geologic record, as opposed to the one that we are going to see currently today in the rock record later on. And this is generally how we separate out the different geologic periods, right? So the Cambrian is kind of the only one that is differentiated from the Precambrian by an explosion of life. And then everything else is mass extinction events that end eras and begin new ones. And this is where the Permian falls on the geologic time scale here. And you can see that marks the end of the Paleozoic. So that's the boundary between the Paleozoic and the Mesozoic. So this was mostly ocean life and some land life, the rise of reptiles. Then the Mesozoic is really the age of reptiles, right? So that's the Triassic, Jurassic, and Cretaceous. One last thing about the Permian extinction, estimated that 96% of marine species and 70% of land-dwelling vertebrates were extinct. And that's a slightly different number than the slide before, where we were just looking at the diversity of different families. But overall, something close to maybe 80% of all life actually disappeared as far as actual organisms on the planet, regardless of what family they fell into. Many famous organisms like sea scorpions and trilobites were never seen again in the fossil record, so trilobites gone after that. And the leading theory here is that the Permian extinction was caused by widespread volcanism. And what this widespread volcanism probably would have done is put enough particulates up into the air through ash and dust that it blocked out the sun and caused a major cooling event. And many of these species had evolved in warm climates and warm oceans, and they couldn't handle that sudden drop in temperature, and so they died out. But this did usher in the age of dinosaurs, so ushered in the Mesozoic. Here's a quick figure for evidence of that volcanic activity. Here we see these blue splotches here. So these are all flood basalts that erupted during this time, and they're all over the planet. Although at the time, these continents were not where they are today. If you look back at a previous slide, you'll see they were all kind of locked up in that supercontinent. But there would have just been massive volcanism for whatever reason, and all of these kind of have been absolute age dated to exactly the end of the Permian. And so this would have been enough to severely alter the composition of the atmosphere and the temperature, enough to cause that Permian extinction. So for the Mesozoic, or age of dinosaurs, it's divided again into 3 main epochs. That's the Triassic, Jurassic, and Cretaceous. This marks the breakup of Pangaea. And organisms that survived at the end of the Paleozoic extinction diversified to fill the biological voids left by extinct species. And this is a common theme that we see in any mass extinction event. Whoever was left over crawls up out of the rubble, so to speak, and suddenly there's a lot more food for them, because whatever was outcompeting them before has died. And so they're able to exploit ecological niches that they weren't able to exploit before. And we saw that with land lizards mostly, exploiting like the smaller land lizards and lizards with certain types of body shapes and sort of adaptive qualities were able to exploit those niches. And so therefore dinosaurs eventually became the dominant species and thrived throughout pretty much the entire Mesozoic. So in the Triassic, much of the world's land is above sea level, right? So most of the continental crust is above sea level, probably due to that cooling event at the end of the Permian, where you would have had maybe increased glaciation, so sea level dropped. And so much of the land was exposed, and this allowed species to really get a foothold there. In the Jurassic, sea started to invade western North America, and much of the land in the American Southwest is desert. And in the Cretaceous, then we had tons of swamps over much of North America, creating much of the Cretaceous coal deposits that we see. And so this is a kind of a snapshot of what that would have looked like. If you've ever been to a museum, you've probably seen some dioramas of this. Lots of club mosses, lots of ferns, giant insects, and sort of a few dinosaurs still kind of hanging out there at the end. So here's a brief overview of Mesozoic history. So we had the breakup of this supercontinent Pangaea starting at about 200 million years ago. This is the early birth of the Atlantic Ocean. So here we see North America and Asia and South America and Africa were very much connected here during Pangaea, but they started to rift apart and started to separate out. And at about 150 million years ago, during the late Jurassic, we started to really see those seas start to open up. And Laurasia and Gondwanaland beginning to separate. Then cut to the Cretaceous at about 100 million years ago. Our planet's starting to look a little bit like we know it today, with some notable exceptions. India is still all the way down here. It hasn't made its way up here yet and crashed into Asia. Australia is still connected to Antarctica, and both of them are very much at the South Pole. And so Australia at this time would have been probably an icy continent. But everything in the southern and northern hemispheres above those two are really kind of where they are equatorially, where they are today as far as latitude. Okay, and then at about 50 million years ago, during the early Cenozoic, which is our era, the continents are really starting to take shape. So India is about to collide into Asia. Australia is starting to make its way up to lower latitudes. The Tethys Sea, which would be the entire sea around Pangaea, begins to close as the continents spread out. So that's notable. North American plate is starting to override the Pacific plate, so we're starting to get subduction at the western edge of North and South America. And igneous activity starts to form the California ranges during this time, and the rocks in the Sierra Nevadas and Cascades. And the middle and southern ranges of the Rocky Mountains start to form in the Western Hemisphere. And that stretches down through Central America and into the Andes as well. So as far as Mesozoic life, the survivors of the Great Paleozoic extinction, so the Permian extinction, diversify, again, like I said, to fill those biological voids. The species begin to adapt to drier climates as those continents are moving away from the equator. Gymnosperms, like early ancestors of pines, firs, junipers, and ginkgos, become the dominant trees. And reptiles start to adapt to drier conditions. They become the first true terrestrial animals and the dominant land animals. And it's important to note that amphibians, they lay their eggs in water, right? And they're sort of the evolutionary step before reptiles, so to speak. Once reptiles begin to have their young on land, they haven't evolved live birth yet. And so what an egg really is in this case is it's recreating the conditions of the ocean, but encapsulated into a little package that can be delivered on land. So really what eggs are like little mini oceans for the early embryos of reptiles to develop. So they can travel much further inland. They don't have to be near oceans or large bodies of water, and this is all just part of them adapting to the drier climate. Okay, and you can imagine that this would have been an early mutation. Maybe just one day there was some reptile-like, amphibian-like early ancestor of reptiles, but a true reptile that had a baby that just had a little bit of a mucousy kind of layer around its egg. It didn't quite land in the water, it landed on land, and it survived. And it has the genetic material that carries that mutation, and so its offspring also have that same kind of membrane. And then over time, further mutations allowed that membrane to develop into something like an egg shell. And this is happening over millions of years, mind you. And eventually we get eggs as we know them today. So reptiles were the first egg layers on land, and when the common ancestor between reptiles and birds branched off, birds carried that egg-laying trait with them, whereas mammals did not, and so we don't lay eggs, with the exception of echidnas and platypus, right? So Mesozoic life, again, dominantly reptilian. Reptiles quickly diversified into different groups, including pterosaurs, which are flying reptiles, plesiosaurs, which are marine reptiles, so they evolved on land but then returned back into the ocean, and many of their body parts that were legs and arms, or I guess just legs, started to look more fin-like, so much like whales and dolphins did later on. Some things can evolve on land and then return back into the ocean, so that's the plesiosaur. And then dinosaurs. We tend to think of all of these as dinosaurs, but dinosaurs are separate from pterosaurs and plesiosaurs, generally speaking. And then we have a mass extinction at the close of the Mesozoic. And dinosaur ancestors that survived would be turtles, snakes, crocodiles, other lizards, but dinosaurs, plesiosaurs, and pterosaurs disappear. So here's the late Mesozoic. This is what it would have looked like. Here's all your dinosaurs and pterosaurs kind of on land doing their thing. Here's your plesiosaurs down here, plus sea turtles and things like that. And of course, fish are still around and invertebrates are still around. But at the end of the Mesozoic, there was an extinction event that wiped out the largest and most abundant forms of these different lizards. Here's what their evolutionary tree looks like. So any reptiles during the Paleozoic, we would just call them stem reptiles. But then at some point, there was a common ancestor that began to branch into plesiosaurs, ichthyosaurs, turtles, then some stem that had a common ancestor between lizards and snakes. And from those common ancestors, you also get pterosaurs. You get a common ancestor from pterosaurs to dinosaurs and crocodiles. Then there's a later branch of just crocodiles and dinosaurs. And then at some point, there's a branch that leads to birds. Then we had therapsids, which had a common ancestor with all of these guys. And from that common ancestor, these therapsids began to evolve, and they were the reptiles that looked a little bit more like mammals. And at some point, there was a branch to true mammals, and therapsids died out. But here, let's look at the 65 million end of the Mesozoic here. This is where plesiosaurs, ichthyosaurs, pterosaurs, and dinosaurs all died. Therapsids would have died before that, and what carried on were the reptiles that we see today and mammals and birds that we see today. So what was the cause of the extinction of the dinosaurs, pterosaurs, and plesiosaurs? Well, over here on the right, you'll see a cool meme I saw a few years back showing exactly what it is that did dinosaurs in and allowed mammals to rise up after. So at about 65 million years ago, we had this major extinction event, likely due to a large meteorite impact. This would have been about in the near the Gulf of Mexico, near the Yucatan Peninsula. Dust and debris from this restricted sunlight and limited photosynthesis, causing a collapse in the food chain. Things were able to survive, but nothing as large as dinosaurs and other large animals, which need tons of food per day to survive, and a collapse in the food chain, they're going to be the first to go, right? Because they require a lot more caloric intake daily to survive, and that stuff just wasn't around, and so they died off pretty quickly. Although it should be noted here, many paleontologists were looking at sort of environmental changes that were happening during the end of the Mesozoic anyway, due to the divergence of the supercontinent into the smaller continents, and probably there were climate changes that were happening, and maybe the dinosaurs were already on their way out at this time, and this impact was really just the straw that broke the camel's back. But regardless, evidence for this meteorite comes from this uridium-rich layer of sediment along the Cretaceous-Paleogene or Mesozoic and Cenozoic boundary, and this is known as the KT boundary. And this was discovered by these two heartthrobs over here, the Alvarezes. This is Luis Alvarez and his son Walter. And they discovered, when they were looking at sedimentary unconformities between different rock layers, they were actually doing a slightly different study, but they came across this uridium-rich layer that they sampled. And they brought it back. They found out that it was indeed uridium-rich, which is a signature of meteor impacts. Meteors carry uridium, and when they impact, they basically vaporize upon impact. Some of it is incorporated into the crust, and some of it is expelled into the atmosphere. And that uridium that's expelled into the atmosphere eventually will settle down and fall on exposed rock on the surface. And then other sedimentary layers will later come during other, depositional events and bury that uridium layer. And what these guys found was that as they traveled all over the planet, they found this uridium-rich layer in the exact same aged sediments all the way across the world. And so this would have been a massive event that affected the whole planet, where uridium was able to travel through the atmosphere across both the northern and southern and western and eastern hemispheres. And what this did was show us that below the KT boundary, 0 dinosaur fossils. Okay? Or sorry, let me rephrase that and say it correctly. Below the KT boundary, that uridium layer, tons of dinosaur fossils. Above the KT boundary, no dinosaur fossils, and lots of mammal and bird fossils. Okay, and very few mammal fossils below, right? So really this is the mark of that boundary. And so here we have dinosaurs. They're eating most of the stuff here. I don't know, this is a brachiosaur maybe, or a Diplodocus or something like that. But then all these little guys, these birds and mammals, they're just over here kind of eating scraps, right? Because dinosaurs were really running the show. Once the dinosaurs are gone, all these guys here, they decided, well, now we can move into these other areas and we can start to eat all the stuff that the dinosaurs were eating. And these couple of fellas down here, I want to introduce you to. They're this kind of shrew-like creature, and they are great times 10 to the 50th grandparents. So these are the common ancestors of all primates, all mammals in general. And so these are the common ancestor between you and your dog and a giraffe and a whale and you name it. So these are our long lost relatives here, and we're lucky that they were around. And this ushered in the Cenozoic era, which is the age of mammals. So this is Cenozoic means era of recent life, and it encompasses basically the last 65 million years of Earth's history. Most of the physical landscapes and life forms that we know of came into being during this time. We have a much better geologic record of this time as the rock formations are widespread and less disturbed, right, because they're younger. And we divide this into the Paleogene, which is the first 42 million years of it, the Neogene, which is the following 23 million years, and then the Quaternary, which is the last 2 million years. And the dominant feature of the Quaternary is the rise of humans and different Homo species, and lots of glaciation, so lots of ice ages, most of which we studied in the glaciers portion. So this is the age of the Pleistocene here. The Cenozoic in North America. So in North America, most of the continent was above sea level. In the eastern North America, we are tectonically stable now. So we would have had tectonics at some point over here. We would have had subduction, but that's long since dried up, and we've formed what we call a passive margin here, where any movement of the plate now is being driven by seafloor spreading in the middle of the Atlantic at the divergent boundary that we still see there today. And so there's no longer an active plate boundary between the Atlantic crust and the North American continental crust. So this is a passive margin, but because of ocean sediment building up here, we still have some effects, okay, on the eastern part of the continent. The western North American continent is the leading edge now, so it's where there's still tectonically active stuff happening, and that is that, as we know, the Pacific crust is subducting over here underneath the North American crust, and so that's the active margin, and we get all the volcanics and stuff that we would expect to see there. And in the eastern North America, we have abundant marine sediments, like I said, causing a sort of down warping of the crust, producing faults and folds, and those faults and folds are trapping a lot of natural gas and oil. That's why we see a lot of natural gas and oil over there in the marine sediments and in the Gulf of Mexico as well. The original Appalachians would have eroded down to a low plain, but because of isostatic adjustments, those regions start to raise up again, and streams begin to erode and sculpt the surface into the Appalachians that we see today. And in Western North America, we've got crustal movements that form these kind of fault block mountain ranges. This is the basin and range provinces that we see in Nevada, Utah, New Mexico, Colorado, places like that. You're getting a lot of uplift, so it's re-elevating the Rockies. And you're also getting a lot of erosion through river systems due to that uplift, and that formed the Grand Canyon. So the Grand Canyon really formed in kind of the last 65 million years. We also had a lot of volcanic activity. So we had flood basalts in the Columbia Plateau. We had stratovolcanoes in the Cascade Range due to subduction. We've got deformation near the coast of the Pacific and the Sierra Nevadas forming from that fault. So most of Western United States all kind of formed during this time, right? So that's why they're the younger of the two major mountain ranges we have in North America. And then we have the late Neogene, which is the final 2 million period, and that's the rise of humans. The Homo species, starting with some of the earliest ones like Homo habiliensis, Homo erectus. There's a whole bunch of them back there. They evolved during kind of times of more glaciation and other erosional events, right? So we begin to sculpt the landscape a bit in the last few centuries, but humans have been around for much longer than that. Humans, modern Homo sapiens have been around for about 250 to 300,000 years. The Homo species has been around for about 1.7, 1.8, maybe even 2 million years. And this includes, like I said, Homo erectus, Neanderthals, so Homo neanderthalis, and then a bunch of subspecies that I encourage you to read about. There's some mentioned in your book. And also, if you're really interested in this particular chapter of the class, I want you to think about maybe taking GL 104 in the winter. That's historical geology, where you basically take everything I just talked about in the last hour and break it up over a whole semester. And you really do a deep dive into everything that we've learned here. So if this interests you at all, I highly recommend it. And there's a lot of covering primates and primate evolution, the evolution of the great apes, and us. So some major milestones in the Cenozoic. We've got angiosperms, so that's flowering plants that have fruits and flowers and that cover the seeds. This replaces gymnosperms as the dominant land plant. Mammals and birds co-evolve with the evolution of these angiosperms. Many primates were tree-dwelling to begin with, and that was to get a hold of many of these fruits and things that are packed with lots of calories and lots of sugar. And so primates and apes and monkeys all evolved, co-evolved with flowering plants and fruit-bearing plants. Similarly, grasses began to evolve, and so we get more grassland mammals beginning to evolve, and then sort of carnivorous predators that feed on those herbivore grassland mammals. So this is really where mammals begin to take off, and birds as well. And mammals and birds replace reptiles as the dominant land species. And this is when, again, like I said, primates begin to evolve. And this is an early Eocene, so 45 million year old primate. This is the common ancestor of all primates on land. So this is the common ancestor that we share with our ape cousins like chimps, orangutans, bonobos, gorillas, etc., and also monkeys. Eventually, the apes will lose their tails, and monkeys hold on to them. And there's some other changes that happen there. But this is the common ancestor, Eosimius, right? Our kind of simian ancestor. So the distinction between mammals and reptiles. Mammalian young are born live, right? They have live births, no shells, no eggs. Mammals are warm-blooded, so they can maintain a more steady body temperature, and they can lead more active and geographically diverse lives. So we can exploit, because we're warm-blooded, we can exploit more terrain and different climates on the planet. Lizards don't live in Siberia, but humans get along just fine up there. We scrape by a living, especially since we can we developed culture and with it clothing and things like that. And then mammals developed insulating body hair and more efficient heart and lungs, so we're able to push oxygen and heat and warm blood to our extremities much more efficiently. And this allowed us to exploit environments and also grow quite large for a time. And that's what we see here with the megafauna, like mammoths and giant sloths and saber-tooths and things like that. And with that, we're basically at the present day. I would really encourage you to watch this video. So go ahead and on the lecture slides and click on this link here. And it's basically everything that I just talked about in the last hour and 10 minutes, all slammed into one kind of 2.5 minute movie. It's definitely worth watching, and it kind of seals the deal and sort of helps it sink in, I think. I can't remember where I found it, but it looks like something from a show on National Geographic or the History Channel or something like that. But go ahead and give that a watch. And with that, we have concluded all the lectures for Geology 101 for this section. It was a lot to cover, and I'm really proud of you guys for sticking with it and keeping up with the pace of this class. And you all did a really, really good job. And if you have any questions on this, let me know. The lab that we do on Earth history is more looking at Earth sediments over historical time in the bedrock here in Michigan. We don't really get into life evolution too much, so in lab anyway. So if you have any more questions about this, definitely let me know. And if you're interested in that GL 104 class, I have some more information about that as well that I can give you. I have a little handout for you. And with that, I'll go ahead and sign off. It's been a real pleasure. I'll see you guys in the last couple labs. And as always, enjoy yourselves and have a great day. Take care now.